The C programming language was created in the 1970s by Dennis Ritchie, making it one of the oldest languages still in common use today. Despite its age, it still regularly appears in developer surveys of the most popular languages. And out of all programming languages in existence, C is by far the most deserving of the term load-bearing. C still makes up the lion's share of the most important code in all the major operating systems, database engines, and graphics drivers, as well as some of the most foundational tools and libraries that we rely on, like Git, FFmpeg, the Apache and Nginx web servers, and even the Python programming language itself is written in C. But when you ask the average developer what they think about C, the standard answer is usually along the lines of it's very low level, or it's for experts, or a number of other sentiments that can be loosely summarized as it's scary. People's perception seems to be that C is so Spartan that you need to build everything yourself from scratch, and even if you do that, you still have to survive drowning in an ocean of seg faults and memory errors just so you can deploy an application that will get hacked immediately as the result of a security exploit. And to be honest, if you try and start programming in C based on how a lot of introductory C material is taught, this probably will be your experience. I had to use C in university, and I found it so difficult compared to other programming languages I'd used before. But fast forward to today, and C is the main language I use. I find it very simple and flexible. And in my day-to-day, I don't really encounter any of the issues people normally associate with C programming. And some of that, sure, is down to experience and education, but I would actually attribute most of it to applying a small handful of simple but incredibly foundational tricks that I've picked up from other more experienced C developers. In this video, I'm going to teach you some of my tricks that allow me to have a joyful and satisfying experience programming in C. I'm going to assume you have some background programming knowledge already, either from a different language or from attempting C before, and rather than being a tutorial about how to program in C specifically, this video is more just to help you get started on the right foot. The first tip is that many people don't know there are actually different versions of C, with different syntax and different features. Even though I mentioned that C was created in the 1970s, the oldest version of C still in common use today is from the year 1989, and as a result is called C89, with most C versions being named after the year in which the version was finalized. C89 is the most widely compatible and supported version of C. It can be included and compiled directly as C++ with no changes, and it's supported by an incredibly wide range of compilers for every piece of hardware you could imagine. So if C89 is the de facto standard, then what do the other C versions actually bring to the table? I personally use C99, and it's mainly because I find the syntax of C89 to be quite cumbersome. Unlike almost every other modern programming language, in C89 local variables all need to be declared at the top of the function that they're used in, rather than anywhere you like. I find this especially irritating with loops, because not only does the index variable need to be declared at the top of the function scope instead of inline, but it also means you can reference the index variable I after the loop has ended. C99, by contrast, allows you to declare variables anywhere in a scope. The second major difference in syntax is how you initialize structs. In C89, if you declare a user struct that has an ID, a name, and an age, when you want to initialize one of these structs, the way that you do it is by providing values for each of the members in order. You can think of it as like calling a function. You need to get the parameters in the right order. I have two issues with this style of initialization. Firstly, if you have two consecutive members in your struct that are the same type, there's a risk that you'll initialize them the wrong way around. The second issue is that if you have a number of struct members declared first that you don't care about and want to leave as 0, you still need to write in all the zeros in your initialization because the fields need to be specified in order. C99 adds an extremely useful feature called designated initializers, which allows you to specify your struct members as key value pairs, much more in line with how modern programming languages initialize objects. This way you don't need the members to be in order, and you also don't need to specify any members that you're not using. They'll just be automatically set to 0. This really is a huge quality of life boost for me, and this alone is enough for me to use C99. The third issue I have with C89 is the types provided by the language can actually vary in size in terms of the number of bits, depending on which platform you're compiling for. This means that in a modern setting, you can mostly assume that int, for example, is 32 bits, but it's not guaranteed. All the standard says is that ints need to be at least 16 bits. On top of that, I find the names for types in C89 quite unintuitive compared to C99. For example, if you haven't really used C before, pause the video and see if you can match these names to their corresponding sizes. We'll start with something easy. Signed char you can generally assume to be an 8-bit signed value. Long int, on the other hand, on Windows maps to a 32-bit signed int, whereas on Linux and other OSs it maps to a 64-bit signed int. Long usually maps to an int64, which of course means on Linux long int and long are the same thing, and on Windows they're different. Unsigned short would map to an unsigned 16-bit value, and I always had trouble remembering that short was 16 bits. And just plain char, you might assume would map to a signed 8-bit value, but in actual fact char not only can be signed or unsigned, but it's not even guaranteed to be 8 bits. C99 introduced the standard int header, which provides much more straightforward and modern integer type handling. You have types like uint32, int16, uint8, that kind of thing. So not only are they reliably sized across systems, but in my opinion they're much easier to understand. There are also some great utility types in the standard int header, including uint pointer, which is guaranteed to be big enough to hold a pointer on whatever target you're compiling to. And there are also a whole host of convenient constants like the maximum and minimum values of all of these types. There's a number of other quality of life improvements in C99 like compound literals, which means you can define structs inline for function arguments rather than having to define them as a separate variable and then pass them, and little things like adding the standard double / syntax for single line comments. I find all these small quality of life improvements really add up. The difference between C89 and C99 is the biggest jump in my opinion, and C99 is what I personally use, but I'll also include some links so you can learn about the newer C standard versions, C11 and C23. And just as a kind of funny side note, in my experience, people whose only exposure to C was, that one university course where they forced you to use it, chances are that course was taught using C89 and really didn't give you a proper picture of what programming in C can be like these days. The second tip is a very quick and simple one about compiling your code. When I compile C, there are a couple of flags I always use. Firstly, given what we just learned about, we can't forget to tell the compiler which version of C we actually want to use. I'm setting the standard to C99, but of course you can choose the version of C that works for you. The second flag is WALL and turns on significantly more optional warnings emitted by the compiler. A C compiler warning is just a message that the compiler will print to the console when you're compiling your program, and can not only help you catch mistakes, but if you're not that familiar with C, it can also help you learn what is a mistake in C. And the last argument, WError, takes all those warnings that you've switched on and promotes them to compiler errors. So in this case, Clang will actually refuse to compile my code if there are any warnings at all. And I find that switching these on from the very beginning of a project helps you keep those warnings under control as you work. Now that we're thinking about compiling code, the third tip is how to organize your C projects structurally. As every programming project becomes larger and more complex, eventually you're going to need to use more than one file for your code. Pretty much every single programming language has a different way of managing multiple source files and building them into a single executable. But in C, you typically do it via this convoluted process of splitting up files into .h header files and .c implementation files, and then only including header files, and using the compiler or a build system to compile the C files separately and then link them together. This is one of those things that can become so complicated that it even has a name, which is include hell. And when you look online for people's recommendations on how to solve this problem, they usually tell you about some kind of automated build system which has its own complexity and learning curve. And this is all just because we wanted to use more than one file. I personally find that dealing with this antiquated system is one of the biggest bumps in the road for people who are new to programming in C. And that's a shame because most of it's just convention and not actually a requirement. All that the include directive does in C is read a file off the disk and literally paste the contents in at the line of the include. If you want to see for yourself, you can actually tell the compiler to save the state of the interim file with the includes pasted in by using the save temps flag. It's quite useful for figuring out include and macro expansion problems. If you wanted, you could include a JSON file and it would literally just paste the contents of the JSON file onto the line of the include. It almost certainly wouldn't compile, but you can do it. You don't even have to use the .h or even .c file extensions, they're just conventions too. You can call your files .whatever if you want. And you'll find this kind of thing is so common in C. These things that you would assume are rules enforced by the compiler or the language, and they're actually just conventions that people have adopted over the years. And so given that all include does is read a file and paste it into your source code, you can potentially see a problem here already. If you include a file twice, you can end up with duplicate symbols, function definitions, global variables, all that kind of thing. Now, of course, there are a whole lot of tricks and tool sets and techniques for helping you deal with these problems around include, but because I tend to gravitate towards simple solutions, I actually just avoid the problem entirely by using what's called a single translation unit, otherwise known as a unity build. The way that this technique works is that instead of compiling all your C files separately, using headers to expose function prototypes and linking them all together, you just include all your C files in order at the top of your main file. All the functions and symbols in your program are available for you to access, and even for large programs, you can avoid having to use a build system at all. You just compile your main C file with a single simple call to the compiler, and that's it. I very rarely have to think about or deal with problems related to include these days, and using a single translation unit is a big part of why. After you've chosen a C standard based on your needs and got your C project to compile and run, the next biggest quality of life improvement is using a debugger. If you're using a modern scripting language that has a garbage collector, an interpreter, and decent reflection, you might be on the side of thinking, well, I can just use print statements to do my debugging, that will work fine. I can tell you right now that that will just not work for you in C. You absolutely need a debugger, not just to be productive, but to stay happy. Even if you've never used C before, I'm sure that you've heard of the dreaded seg fault. Seg fault is short for segmentation fault, and although segmentation fault sounds like some complex low-level computer thing, they're actually very simple. When your program starts up, the operating system assigns your program a very large virtual address space that starts off completely empty, and all of your pointers are just indexes into this address space. We'll label the addresses from 0 to 100 just for simplicity in this case. So your executable code gets loaded into memory somewhere, and whenever you call a memory allocation function like malloc, underneath the OS will map the memory you asked for somewhere into that virtual address space. If you try to read or write to an address inside that allocated space, everything works fine. But if you try to access memory outside of those mapped regions, you'll get a seg fault. Which of course now makes it clear why reading from or writing to a null pointer causes a segmentation fault. Null on the majority of systems is simply defined as 0, which almost always maps to an invalid virtual address. Problem is, a null pointer is just one of an enormous number of ways that you can access memory that you weren't supposed to, including accessing an array out of bounds, messing up pointer arithmetic, freeing memory and then trying to use it again, the list goes on. If we take our simple null pointer program, compile it from the command line, and run it, the program unceremoniously crashes and the OS prints segmentation fault to the console. No line number, no explanation of what caused the crash, nothing. Just segmentation fault. You can see why this error message has such a negative reputation, right? But if we jump into an IDE that supports a debugger, watch what happens when I run the program with my debugger attached. Instead of just crashing with a seg fault, the debugger pauses right as I make the illegal memory access. Not only can I see the exact place the error occurred, but I can see the entire call stack of what led to that function being called, as well as inspecting the state of all the local variables. I can take a look here and see, oh, my pointer that I tried to follow was null. For the vast majority of the projects that you might work on, you should be able to just run your application in debug mode with the debugger attached all the time, and the performance impact won't really be noticeable. But for that small percentage of projects where it does matter, You can actually just compile your program in release mode with debug info and still be able to catch seg faults and other memory errors in the debugger. Most of the fully fledged C development environments like CLion or Visual Studio have a built-in debugger that you can use, but there are also some fantastic standalone debuggers that run as their own application, like RemedyBG and RadDebugger. So now we're running with a debugger and can easily diagnose those types of memory access violations. But there's something in C which is much more scary than a seg fault, and that's memory corruption. As we discussed, seg faults occur when you access memory which is outside of what's been mapped into your virtual address space by the operating system. But sometimes you make a mistake, and instead of the mistake causing you to access memory outside of your valid address space, instead you end up accessing or overwriting memory from some other valid part of your program, which doesn't cause a seg fault because it's technically a valid memory access. This can cause bizarre and very hard to diagnose issues. There's a popular Cain video that I'll link in the description about the development of the first Fallout game, where he describes this hellish process of chasing a memory corruption bug caused by a tiny off-by-one mistake in code. One of his co-developers, Mark Harrison, came up with a very clever idea for how to narrow down and find this memory corruption. And 25 years later, we not only have an amazing set of tools that works in a very similar way to the ones that they used on the Fallout project, but we also have enough compute power to have them switched on all the time. Which brings us to tip number 5, which is about a set of tooling called address sanitization, often referred to as ASAN for short. ASAN is designed to help you catch memory corruption issues, and to explain how it works, I'll give you an example. Say we're calling malloc and asking for enough memory to store 10 integers. This is the classic C way of creating an array on the heap. C, like almost every other language, has the square bracket syntax for array access, but C's arrays have no built-in bounds checking, which means that inside our square brackets we can put any number we like, and there will be no runtime checks to make sure we're not accessing outside the bounds of our array. If I try to access some huge index like the maximum of a 32-bit integer, we get a seg fault because we're accessing outside of the valid range of memory that the OS has mapped to our process, which is caught by the debugger. We can see the exact line where the bad access occurred, so it should be an easy fix. But this won't always happen. When you call malloc requesting something like 40 bytes, under the hood, both malloc's internal allocator and the operating system are actually mapping some minimum size block of memory that's at least the size you asked for, and more than likely larger than what you asked for. And the reason that's important is, if we replicate Tim Kane's Fallout bug and iterate through an array writing to each element, but we accidentally used less than equal rather than less than for our comparison, we end up writing data to an address just one off the end of our malloc array. But because behind the scenes, the memory that was allocated by malloc in the OS is larger than just the 40 bytes we asked for, 4 bytes past the end of this array is actually still valid memory in our program's address space. So we don't get a seg fault, and the program just continues on with silently corrupted memory. These are some of the most fiendish and difficult bugs to diagnose. Silent corruption often isn't detected until someone sees something visually strange happening, which is often a long time after the corruption actually occurred. And of course, they can happen randomly and non-deterministically on each program run, depending on how your heap is laid out. So an address sanitizer is designed to help us catch these types of problems. The most famous modern-day one was developed by Google, but now they're built into most modern compilers. In Clang, for example, you can turn it on with a flag, fsanitize equals address. And when I'm doing local development in C, I basically have this flag turned on all the time. What an address sanitizer does is hook into calls to malloc and insert special data into the memory around the boundaries of your allocations. It then observes reads and writes to those special regions of data, because that indicates that your program has done something wrong. If we switch it on for our loop condition bug, we can see that now the address sanitizer immediately catches our out-of-bounds access and pauses the debugger on the line where the invalid memory access occurred. As always, we can see a full stack trace, inspect the state of local variables, the works. I find that this makes certain types of memory mistakes trivial to debug in practice, compared to trying to reverse engineer or reproduce them. ASAN and the debugger are your two biggest allies when dealing with memory in C family languages. But of course, ASAN doesn't come without a cost. All that memory observation is going to cost you performance, and you don't want to ship your application with ASAN still switched on. As a result, any of these memory errors that ASAN can detect have to be caught in your local development environment or your testing environment, because when you compile for release and switch it off, you're still not going to have any bounds checking. Which brings me to tip number 6, which is about arrays and that is very pink. I'm sorry about that. As I mentioned previously, arrays in C are generally indistinguishable from pointers. All that an array really is in C is a pointer to a single piece of data of some type in memory that the programmer assumes is followed by a certain number of objects that are all the same size. And when I say the programmer assumes, what I mean is that the programming language itself has no concept of how many items there actually are. In addition to the inconvenience of having to track the length of the array yourself if you want to iterate through it, this also means that C does no runtime bounds checking on array access. And as we've seen, you can easily just mess up your index calculation and end up with a memory bug. I personally consider runtime bounds checking to be essential in 2025. There may have been a world in the past where the performance concern was legitimate, back when CPUs were very slow, before optimizing compilers got smarter, and before CPU branch predictors existed. But nowadays, I think you have to have an incredibly well-measured and justified reason for having no bounds checking at all. But the good news is, because C is such a wonderfully simple and flexible language, implementing runtime bounds checking yourself is incredibly straightforward. I tend to always start with the simplest approach I can think of. All my arrays are defined as a struct that stores at least the current length and the total capacity, in addition to a pointer to the first element. These structs can be passed around as a single function argument and provide a great starting point. But we still have the problem of accidentally accessing our array out of bounds. All it takes is passing a bad index into the square brackets. ASAN might catch it in your local environment, but you can't rely on testing every possible combination of input locally. So what we really want to do here is implement some kind of runtime bounds checking on our array accesses. I've seen people do some macro magic to achieve this kind of thing, but I personally like to use the simple, straightforward approach because it helps me understand how things actually work. I just write a get function for my array that does the bounds check and call it something like intArray get. If the check doesn't pass and the index is invalid, I'm just returning some default value here. But on top of that, I'd almost always have a debug breakpoint set in this error branch, so the debugger will automatically catch if I try to access something out of bounds, the same as it does with ASAN. And if you don't want to set the breakpoint yourself, there are platform-specific functions that you can call that will automatically pause any attached debugger. Calling a get function like this is actually a lot more convenient than it seems on the surface. With any decent modern IDE or C language server, I can just type the name of the array variable, hit the dot key, and you can see that autocomplete will suggest the get function for me. And this isn't some AI magic. Modern IDEs for C will autocomplete any function that takes the type of the variable as the first argument. You can see when I press enter here, it not only autocompletes the function call, but it puts my array in as the first argument and puts the cursor into the second argument, so I can just type I here and I'm done. Now, it probably feels like it will add some overhead calling a function on every iteration of our loop like this, but you'll be pleased to know that because we're in a loop that's going from 0 to length -1, and the check also tests those same boundaries, modern compilers are actually smart enough to just optimize the entire check out when compiling in release mode. On top of that, because accessing an array out of bounds is indicative of something going very wrong, if your program's executing correctly, this branch will always go the same way. That is, the check will always pass, which means the CPU branch predictor is going to reliably guess which way this check is going to go. Something you might have picked up on looking at this code is that the structure and function I've written for my array has a specific type. If I try to pass a different type of array to my get function, the C type checker will catch it. So does that mean I need to write a separate struct and function for every type of array I have? In short, yes, you do. C doesn't support generics in the modern sense, so rather than writing a lot of boilerplate, a classic C approach to this problem is to do something like make a function that takes a void pointer, that is, a pointer with no type, and then pass the size of the array item type as another argument, potentially wrapping some macro around it to make it more pleasant to use. And don't get me wrong, there are some amazing generic array implementations using macros out there that are very well designed, like Sean Barrett's STB array, which I'll leave a link to. But for me personally, I started out by just copy-pasting the code when I needed a new array type. Then when that got a bit too cumbersome, I just spent an hour hacking together a very simple template code generator in JavaScript that can spit out these definitions for me. Feel free to just pick an approach that works for you. So giving your C arrays a length and runtime bounds checking is amazingly helpful on its own, but perhaps the case where it makes the biggest impact is with strings. When you think about it, all a string is just an array of characters. And because we use strings everywhere and processing strings is so common in programming, of course the C standard library provides functions for dealing with strings. But given that arrays in C have no built-in length or bounds checking, how do those library functions actually work? You may or may not know this already, but the convention in C for working with strings and the way that most of the string functions in the standard library work is that there's an assumption that at the end of your string there's what's called a null terminator, which is just a 0 byte, that is a character with the code 0. As a result, if you call the standard library function strlen, which is short for string length, the only way it can figure it out is by following the pointer to the first character and then iterating through one character at a time until it finds a 0 byte, indicating that it's reached the end of the string. This is not only very slow for large strings, but it's also very error-prone. If you accidentally forget or overwrite your null terminator, functions like the standard string length will happily just iterate past the end of your string and either give you back the wrong value or just iterate into uninitialized memory and segfault. If you look up the string length function in a search engine, you'll see that pretty much everyone is confused about whether the length returned includes the null terminator or not, which makes it way too easy to copy the string and forget to include it. The list goes on. This is only the very edge of the rabbit hole when it comes to string handling in C, and I would very strongly advise you avoid using standard library string functions wherever you can. So what's the alternative? Well, it's exactly the same as handling an array. You just define a struct to hold your C string and an integer to store the length. You can then pass your string with its associated length, iterate over it much more safely. Obviously, you can instantly query the length instead of having to iterate through all the characters, and you don't need to rely on null termination at all. A less obvious but amazing benefit that you get from an approach like this is the ability to create string slices. A slice is essentially a string that doesn't own its memory, and in terms of what that actually gives you in practice, imagine you have a large piece of text that you want to split into lines so that you can wrap the text and render each line separately. With null termination, you have no choice but to clone the memory for each line so that you can append the null terminator, otherwise you'll end up messing with the original string. But if you have a length with your strings, you can just create a new slice that points to the first character of the line in the original text with the length of the line. No copying, no null termination needed. Of course, if you use this kind of approach, you will have to write your own string functionality for handling common operations like concatenation or comparing two strings together. But I found that to be pretty simple, and I just build the new functionality as I need it. And besides, building this kind of thing is really the fun part of programming, for me at least. The next tip is a quick one about pointers. When you want to store some kind of relationship between two objects, a very common way to do that is to store a pointer to object B inside object A. This might mean having a struct member that points directly to another struct somewhere, or alternatively, sometimes we need to store an array of pointers, for example. This approach has two major issues. The first one is if the object you're pointing to itself is stored in an array, what happens if the array gets too full and needs to be resized? The data is going to get moved somewhere else, and now you have what's called a dangling pointer. The second issue, if you're pointing to an object in an array, is because C pointers are a self-contained concept, you can load the data from the pointer by dereferencing it without the array that the object's stored in ever knowing, essentially circumventing all the bounds checks that you might have put in. We can solve both these issues with one simple solution. If we want to reference an object in an array, instead of storing a pointer to the object directly, we can store the index of the other object in the array. The first obvious benefit here is that if we're on a 64-bit system, we can save at least 4 bytes per reference because we can use a 32-bit index rather than a 64-bit pointer. This might not necessarily make a difference in struct fields because of alignment and padding, but if you have a packed array of indexes, it's going to be half the size compared to an array of pointers. The second benefit of using indexes is that if the referenced array gets full and needs to be resized, the index will still be correct, because when we resize arrays, we copy the old data into the same indexes in the new array, just with more space at the end. It also means that to resolve this index into an object, we can go through the bounds checking machinery that we set up earlier, which not only gives us much better safety, but calling a function also gives us an opportunity to detect situations where the referenced object has been deleted. I won't go into handling deletions with this approach in detail, but I'll link you some great material on how to approach it, and the keywords you want to be searching for here are generational indexes. The last benefit of using indexes that I'll mention is that it makes your data much easier to serialize. If you have an array of indexes that behave like references to objects in your user array, you can just dump those two arrays straight into a binary file, and when you deserialize them, that is, when you restore them to memory, all those indexes are still going to work because they're just offsets into an array. By contrast, if you have an array of pointers to user objects and you serialize it, close your program, and then restore it again, all those pointers are going to be broken. And that's because pointers are an absolute address in your program's virtual address space, which gets randomized every time your program opens for security reasons. The final tip is about memory management in general. When people first start learning C, one of the most common approaches to managing memory is just to use malloc for everything, and then trying to keep track of when the memory needs to be freed. I've found this to generally be a losing battle, and probably the biggest source of unnecessary fear around memory management in C. In short, you want to be thinking of malloc and similar as building blocks that you can put your own allocators on top of. I have a video where I talk about the concept of allocators in general, as well as another one that talks about a special and very useful type of allocator called an arena. But I'll quickly explain what both of those things are and how they relate to C. When you allocate memory for a variable, we consider that variable to be alive, and the time between when a variable is allocated and when it's deallocated again is referred to as its lifetime. If you individually malloc and free every single variable in your program, you're implicitly saying that every single variable has its own unique lifetime. But in the vast majority of software projects, I've found there to only really be 3 major categories of lifetimes that almost every variable fits into. The first lifetime is the lifetime of the program, often referred to as a static lifetime. Variables with a static lifetime are often allocated when the program starts and live until the program exits. Things like the fundamental program state that you always need access to. The second lifetime is the scope of a function. All local variables fall into this bucket because they're all allocated together on the stack when the function's called and all deallocated together when the function returns. The third lifetime is the lifetime of a task. I'm talking about tasks like importing a file into your program, rendering one frame to the screen in a game, or a user working on a particular document and then closing it. Tasks that we perform have a whole host of associated data and variables that are naturally no longer needed once the task has finished. So instead of calling malloc for every individual variable you need on the heap, you can call malloc once with some large amount of memory and use it for something called an arena. All an arena is some memory where you store all your data that shares the same lifetime. In our example of a user working on a document, all the data related to the document, like the underlying text data, where all the wrap points are for the lines, a cache of the rendered glyphs, all that type of thing, can be stored in an arena that you create with a single call to malloc with a lifetime of the duration of the document. When the user closes the document, rather than having to remember to correctly free all your individual allocations related to the document, you just free the arena and you're done. Using an arena not only makes freeing memory much less error-prone, but as it turns out, doing one large allocation and one large deallocation has much better performance than doing lots of small allocations and deallocations individually. And for me personally, this realization that variables tend to fit into a small number of shared lifetimes, that I could allocate all my data at once and deallocate it all at once instead of having to worry about the individual objects, for me was such a mindset shift around how I thought about memory management in C that it's really comparable to when I first learned that instead of having to copy-paste code, you could just put it into a function and call it. I can't overstate the impact that it's had on my C programming. So I hope that gets you started off on the right foot. When I first started to learn C for my operating systems course in university, I really found it quite aversive, but over the years it's sneakily grown into my favorite language. So I hope you enjoy programming with C. Good luck. I know you can do it.